Yeah, so as the title shows, we are going to be continuing with where we stopped last week. So we discussed the role of hyperparameter tuning or hyperparameter optimization in machine learning based modeling. So, under our important clarification series, based on the principle of let the data speak. So, let the data speak connotes the fact that you use a particular algorithm to solve problem excellently doesn't mean that algorithm will do it for another data set, even if they are from the same area. So that is why we always have to check what is the appropriate algorithm that will work for us and which hyperparameter we produce the needed result that we actually looking towards. So we always first start by referring back to this usual system of the schematic diagram of the modeling pattern. So your data, then you go to the modeling proper, where you have the algorithms. So run it initially, just run the default and see what you can get. Then you see, and then go back. And then the first instance of going back, you need to optimize the hyperparameter. This is what we are concentrating on. Because you can also go back and change the algorithm to another type. But we are not talking about that one. For now, we are seeing if the performance is not yet what you are looking for, you need to go back again and check for the hyperparameter values. See, the same algorithm on two different data sets, they might need different hyperparameter values to get the better result. So we discussed this extensively last time. Most especially, we did mention stage by stage the role it plays in the machine learning modeling process. Now, and we demonstrated for us last time in weaker environment, after letting us realize that it's always a good approach to use the cross-validation techniques so that your model is not centered on a single portion of your data. So the cross-validation techniques, we ensure that you are checking the station of the outcome based on multiple runs using the cross-validation idea, which we've explained before. And we can check out some of our earlier videos on how cross-validation method works. We also mentioned that it's very important to pay attention to it, that you need to check the different combination of the hyperparameter values, which is what we call the hyperparameter tuning. So hyperparameter value is not something we can overlook. The importance cannot be overemphasized, because sometimes we've seen a case whereby you run using the default parameter that comes with the algorithm you are using, and maybe you are struggling to get performance measure in terms of maybe accuracy of 54 after 10. By the time you change one of the hyperparameters, surprisingly from 54, you can move their performance to 95. We've witnessed that before. So now imagine somebody decided to use, because I've seen people made it's a very critical mistake and serious one, to just use default parameters or default value of the hyperparameters. And then you say this is what you have achieved. Even when you achieve 99%. See, we have cases whereby students achieve very high result from one algorithm, but the second algorithm, very poor result, 54. Then we ask, why is this gap? So on further probing, we've noticed that the default parameter for the first algorithm achieved 99% accuracy, and the default parameter for the second one achieved 54. And they just concluded that, wow, since they achieved excellent result in one of them, then they compare the result and they declare that algorithm number 2 is not good for this model, for this data, why first one is good. Say, no, this is not acceptable. This is a kind of a wrong conclusion from your experiment. Because you are declaring that an algorithm that you have not given that algorithm the fair hearing. You see, It's like not giving someone fair hearing and you just declare that person as guilty or not capable of doing what you have asked him us to do. So before you can conclude that an algorithm is not suitable for a particular problem, you must carry out what we call hyperparameter tuning. You have to check for it, check for all the possible values within range. And if after it, you are going to see that as you are changing the value may increase, the value is increasing. Usually you can have a very nice plot to show the result as it is going. So as the value, let's say I'm searching for the value of K, I'm using K nearest neighbor, for example. This is the performance measure, maybe accuracy. So the value is increasing. You started with K is equal to 1. You have 3, you have 5, you have 7, maybe for classification problem. So it was here before, then it became here, got to this level, goes to 7. In as much as it's still increasing, you have to keep trying other values. So we notice after 7, it went down to this. Then you can have a nice plot that shows you that, okay, it means the best hyperparameter tuning for that K is equal to 7. Then you can then conclude that, okay, for K, I've gotten that, but you are not yet done. You have to also search for the other hyperparameter for K nearest neighbor, and that is the distance measure. So you pick the distance measure, you check for Euclidean distance, you can check for Manhattan distance, look at the shape distance, and then you also do the plotting. Maybe in your plot also you come to realize that Manhattan distance gave you the best result. You see, once you get the best result for K, then you are going to keep that K constant while you are changing the distance measure. So at the end of the day now, we achieve K is equal to 7 is the best, and then Manhattan distance measure give us also the best. K and Manhattan distance is going to be our hyperparameter value that we are going to declare in our report, and we're going to use it for our final experiment. It is then that you are fair to that algorithm. So just using default value and then concluding that the algorithm is not correct, no, or it's not powerful enough for that problem, this is not correct. So last time we demonstrated how we can do that. So, and we also made a very slight promise that, okay, we're going to see how we demonstrated for k-nearest neighbor last week. Today, we're going to look into support vector machine as an example. Then after which we are going to look into the using the principle of grid search. Someone asked that question last week. We said we're going to demonstrate also grid search. So doing hyperparameter optimization is not an option. It is compulsory. Once the reviewer find out that you didn't do that, your report or paper stand rejected, actually. Yeah. So because it means someone cannot pick your work and repeat what you have done. And this is one of the points that reviewers are looking for. Your experiment must be repeatable or must be reproducible by someone reading your paper. So if you don't tell us the hyperparameter values you have used, then how are we going to be able to reproduce your work? Definitely it's not possible. So now we're going to look at an example demonstrator now from support vector machine to see how the hyperparameter can also be tuned and which one is very important for us to look out for. As usual, so this is our wiki. You click the Explorer, and then once it is out, so you bring in your data. Before you bring data, everything will be gray out. You can't use it. So we open the file, see an example. So let's go to our, okay, pick maybe issue examples. Yeah, then we have to select the C because you can see here, we can't see any file here. So we have to change here that we are using CSV data file so we can get it. So we open the file. The file is open. So this is the target. So you click the target, you can visualize. So we describe what we have done with this one before. Now, Now, what we want to do now, you go to classify. We demonstrated key nearest neighbor last time. Today, we first of all look into support vector machine. So you can see it under, this is where we have key nearest neighbor under the lazy classifiers. You go to functions, you're going to see support vector machine there. So we're going to look at the very simple one. There's live SVM. It's a kind of a variant of SVM that's implemented a wrapper SVM. So, but we are going to use this very simple one called the SMO. So it also it implements for training support vector classifier. So when you select that, you can see these are the hyperparameter values. So the most important hyperparameter values, we have to check them. It's good to use cross validation to check the hyperparameter optimization. So you're going to go in here. In support vector machine, the most important hyperparameter in support vector machine is the kernel. You can see here, kernel. This is the kernel function. So if we look at the principle of support vector machine, we presented a comprehensive support vector machine some time ago, so we can check out some of our previous videos on how support vector machine was, the uniqueness, and the kernel function actually gives support vector machine a very powerful capability that makes it to be able to avoid some of the downfall of other algorithms. So when you are doing hyperparameter optimization for support vector machine, you have to focus first on the kernel function. So what is the kernel function to be used? So after the kernel function, the next very important one is C, the regularization factor C. Very important also, but that is after the kernel function. Because we've noticed that no matter the value of C you have selected, the kernel function can change the whole thing, because the idea is that it's going to push your data into higher dimension where the data will become separable if they are not separable at the lower dimension. So it provides a very unique capability to make support vector machine achieve excellent result. So sometimes we've often noticed people they just use the default value of support vector machine and they declare that it's not working. No, this is not allowed. This is not correct. Now, so looking at this, let's look at the first one, which is the kernel function we are starting with. So we are going to see, when you go inside, these are the possible kernel function you have to select from. So what you do is, the default value is polynomial. So you pick that polynomial value. You keep the C constant as the default value here is 1. So another hyperparameter for this also is the epsilon. So we'll come back to that later. But I can tell you, once you optimize, you will find the correct value for kernel and C. Epsilon have very, very little effect or influence on the system. But sometimes it depends on the data. Again, this is what we call let the data speak. It depends on the data set. But established procedure is kernel has the most important effect on support vector machine performance, followed by C, then followed by other parameters like epsilon. Like if you are using polynomial option, then the degree of the kernel. If you are using polynomial, what's the degree of the polynomial you are using? Now, for other parameters, these are parameter like number of decimal places. These are normal parameters. They don't really have effect on the algorithm. However, those that have the effect they are known as hyperparameter, like the kernel, like the C. So you're going to keep this constant and start with the most important one, which is the polynomial kernel, which is the default. Okay, then your experiment is ready to go. You are using 10-fold cross validation. So to start running. If the data is big and it can take just some time. Then once that one is finished running, you take note of the value. What is the performance? Maybe we are using accuracy for classification. Let's use accuracy. Now, then you go back. Once that one is done, it's still running here in the background. But assuming it is done, then you go back again, and then you're going to choose the next one. Maybe pre-computed or PUK or RBF. So after polynomial, RBF usually perform also excellently well, depending on the data set you are using. So you have to select each of these options in the kernel function one by one. And then, as we have stated, make sure you always record the result. The result achieved during each of this kind of iteration, you have to put it somewhere. And it's always good to have a very simple plot, like the example I'm showing now. See, put it there, this for your kernel. This is polynomial. Show us, okay, when I use polynomial kernel, this is what I got. So put something there. Now, so this is polynomial kernel. This is RBF and others. So as you are filling it, try to note down the performance. So easily, you can easily plot and see which one is giving you the best value. And then you move on to the other values that you are yet to experiment with. So you change each of them. Once you are done with each and every possible kernel, then the next one is you keep the best kernel permanent. Let's say after all the experiment, we notice that maybe the PUK actually gives you the best kernel value. So you are going to pick that and keep it constant while you start changing the value of C now. You now move down to C. It is time for you to optimize or find the appropriate value for the C, as the case may be. Now you move, then this is 1. Actually, it can even take 0 point something. You can actually make it 0.5 if you want. It's actually between 0.1 and as big as you can think of. So, but usually 10, search for 10, to search for 15, can give 100 sometime. And when you see that this is a simple manual search, check for 100. If you see that you got very low result compared to what you are getting before, you come back to like 90 and check 90. See, maybe I got lower result. That means between 90 and 100 might be where I'm going to start to be able to get the most optimized result. Now, so like I was saying, so we have to keep changing the value of C one after the other, and we are recording what we are getting. In a similar way, we can also make a kind of plot for it to monitor how the value of C is changing gradually from one value to the other against the accuracy. We also make a plot. Yeah, let's say the value of C is gotten finally at 100. You got the best. You keep that one constant again, and then you move to epsilon, and then you start changing the values. So this is how you gradually move from one hyperparameter value to the other until you are sure that we have gotten the best value for this particular algorithm. Then you move to another algorithm that you are doing. So this is an example of how we can search in a very simple manual search. Very simple, and it do work. See, you can see because the data is big, it's still running, so it's going to take some time. Yeah. Because the good news is you can actually create, because I want to mention that, you can actually open several explorer. So you don't need to stick to one. You can open another explorer and then focus on, and then do another hyperparameter optimization there. Open as many as possible, subject to or depending on the power of your machine. And again, this is where group work also helps. So you can also distribute. One of the research team can be working on hyperparameter optimization for one algorithm, while another person works on the hyperparameter value for another algorithm. So by so doing, at the end of the day, you are going to arrive at the best possible hyperparameter values that you are going to use. So this is as regard doing the hyperparameter optimization using the simple manual search, following what we discussed last time. Before we move to the other aspect I promised to touch last time, and that is the one we call the grid search. So let's take note, like I have mentioned, before you can conclude that an algorithm is not working, we have to do the hyperparameter optimization. So this is very, very important. So which method you use depend on your choice. What matter is for you to make sure you have done it as much as possible. So we also mentioned last time that sometimes manual search could be slow. Mentioned it here. The manual search is slow and tedious sometimes, but the better understanding or better the benefit there is that you can understand better how the hyperparameter affect the model. So as they are changing, you can see, you can monitor it easily. And it's good for starter. For those who are just starting, you can be able to see how the system is working practically. Whereas the grid search, which we're going to discuss just later, so will be the one whereby you can automate them, you can set it up, and then you can then come and check later, it will run and then generate your result. So this is for the manual search option.